So as we all know, by the power rule, the derivative of x cubed is, you bring the 3 down, 3x squared. Now, this gives you a relationship between the x cubed and a 3x squared, and I want to take that relationship and I want to turn it on its head. I'm going to talk about something called an antiderivative. So I'm going to say that the antiderivative is the other way around. The antiderivative now of the 3x squared is the x cubed. And then when I say that my x cubed is an antiderivative, what I mean is that if I was to take the x cubed and differentiate it, I'd get the 3x squared. So here's our general definition. We're going to say that big F, we always use big F's for antiderivatives, that big F is an antiderivative of little f if it has the property that the derivative of the antiderivative is just the function. Or to repeat, we're saying this derivative of this antiderivative is the original function. Now, anytime that you have a function and you take its derivative, the function is going to be the antiderivative of the derivative. But it turns out that there's not only one of these things. For instance, look at this function x cubed plus 7. It's also an antiderivative of 3x squared. Why? Well, I claim this is my antiderivative, this is my capital F. If I take the derivative of it, I get 3x squared, and the derivative of 7 is 0. So there's two different antiderivatives for the same function, 3x squared. Likewise, if I added a million, or a billion, or e to the pi to the root 2, it doesn't matter what I add here, any constant that I might choose to add is always going to go away when I differentiate. So that entire infinite family of functions, through x cubed plus any constant, they're all antiderivatives of 3x squared. So we sometimes say this by talking about the general antiderivative, and that we'll say that if you take the derivative of the big F and you get the little f, then the general antiderivative is this big F plus any arbitrary constant. So we have to be a little careful with our grammar. If you have a specific one like x cubed plus 7, you say that is an antiderivative because there's all sorts of them. But then you can refer to the general antiderivative when you write it this way, f of x plus an arbitrary constant c. Now, we'd already investigated what the antiderivative was for 3x squared, but I want to look generally at the antiderivative of just some function x to the n. And my claim is that the antiderivative looks like this. The general form of the antiderivative is x to the n plus 1 all over n plus 1 plus c. But don't take my word for it. Let's verify that this is actually the case. That is, let's take this derivative and see whether we get the x to the n. That's our condition to be an antiderivative. So in other words, if I come along here and I take the derivative with respect to x of this x to the n plus 1 all divided out by n plus 1, well, now that I'm verifying this with the derivative rule, we can use the power rule. We know how to do that. The n plus 1 comes out the front, so it's n plus 1 all divided by n plus 1. Oh, that's good. That's going to cancel. And then x to the power of n plus 1 minus 1, so x to the power of n. So yes, indeed, this is going to be an antiderivative. Now, usually when I'm trying to come up with these antiderivatives, it's a little bit of like a guess and check. I know that the derivative of a power is a different power, but one beneath it. So sort of I thought if I'm going the other way around and it's x to the n, I'm going to have to add 1 to it. So I tried x to the n plus 1 first, and then it was off by this factor of n plus 1, so I divided by the n plus 1, and that's how I got this answer in the end. So a little bit of a guess and check, and that's okay. Okay, let's sort of guess and check again here. The general antiderivative now of sine, I claim, is minus cos of x plus c. Well, don't take my word for it. Let's go and actually compute it and see whether this is the case. So I'm taking the derivative now of minus cosine of x. Well, this minus sign comes out the front, and then when I take the derivative of cosine, I know what that is. It's minus sine. So two minuses, this minus is now going to become a plus sine of x. And indeed, that's what we have. So the derivative of minus cos of x is sine of x. That tells me the antiderivative of sine of x is minus cos of x plus this value of c in the general form. All right, one more of these. I'm going to try to figure out additivity for antiderivatives. We know that the derivative of a sum is the sum of the derivatives. And I want to claim that an antiderivative to the sum is the sum of two antiderivatives. So how might this work? So what I'm going to suppose is that I've got a big F, which is an antiderivative of little f, and I have a big G, which is an antiderivative of little g. Then my claim is that if I want an antiderivative of the sum down here, that the antiderivative to the sum is the sum of these two different antiderivatives, the capital F plus the capital G, plus that C if I'm doing the general form. Okay, so again, we should verify that this is the case. Let's imagine I'm taking the derivative of this bottom here. Well, it's a sum, and the derivative of a sum is the sum of two derivatives, so this would be big F prime plus big G prime, which is just little f and little g. So indeed, we have this additivity property for antiderivatives just as we did for derivatives. And indeed, we're going to want to keep on going through this process and taking all the different rules that we have, the chain rule and the power rule and the scalar multiple rule and so on, and do the same kind of trickery to those. That's going to be coming up in future videos.